All right, so welcome to the second video for Recitation Week 3. In this video, we will be looking at some of these simplicial complexes in MATLAB, specifically using the software JavaPlex. So let me share screen here. So this is JavaPlex on GitHub. It can be found very easy with a Google search, and we'll also have links on the resources section of our course web page on GitHub itself. So here, this is the latest release of JavaPlex on GitHub. So to download and install, JavaPlex is quite simple depending on your operating system. You want to download one of the two MATLAB examples files, and then simply put that put the folder after you decompress it into your MATLAB directory somewhere. And that's all you need to do to install. JavaPlex, one nice thing about JavaPlex is it has a very in-depth and detailed tutorial that you can also find online and is linked on its GitHub page, which has a thorough overview of the functionalities of JavaPlex, also how to install if you need more detailed instructions, though really it is as simple as I described earlier. Also, it has a quick math review of some of these things we have been discussing today, and a large number of examples and exercise problems for you to try out to get to know the software better. Some of the examples that we'll be covering are actually from this tutorial, though there are a number of other examples they have, and I would recommend any of them for practice, just if you want to get better with this software. So some nice things about this software. Well, it's in MATLAB, which is generally considered one of the easier programming languages to learn for mathematicians, and also compared to many of the software packages in TDA, JavaPlex is pretty good in terms of documentation, as you can see here, and also just ease of use. The coding, syntax, there is some upfront learning for sure, but overall it is fairly straightforward. Some downsides are if you go through and check the release history, the software is a little dated now. It hasn't been updated in a few years. And so the main downside there is that compared to some of the newer softwares, it's certainly a little on the slow side. So if you're going to go into, say, industry and be using topological data analysis in practice on very large data sets, you'll probably wind up using a different software. But JavaPlex is very good first software to learn, just to get used to software in TDA and get your feet wet a little. And it still does work very well if you're working in practice with data sets that aren't too large. So now I would request you go ahead and install JavaPlex, and I will see you in a couple moments inside MATLAB. Okay, so now that we have JavaPlex installed and are in MATLAB, it will look something like this. So I went to MATLAB directory and just added in all those files that we unzipped earlier. Here, in the standard file directory would read MATLAB examples. I just renamed that to JavaPlex. So we can see there are a number of different folders which come built in with JavaPlex. There are a lot of these tutorial examples and tutorial solutions, which are from the tutorial PDF that we showed earlier in this video. So if you want to play through, work with any of those to learn more about the software, I encourage you to do so. These files you don't need to worry about. Basic examples or some more examples. And this is the folder where I will keep files for our class, so That's the folder we'll be going into for most of our time in MATLAB. One thing that is very important that you need to do before doing any or running any code which actually involves JavaPlex is to run this function, load JavaPlex. And it just does things in the background. If you try to run code involving JavaPlex but haven't ran the load JavaPlex command since you launched MATLAB, then you'll simply be thrown an error, and you can go back and run load JavaPlex and then proceed with whatever you were doing. So now let's go to some actual examples. So here we're going to do a very simple example of generating the simplicial complex consisting of the two simplex and all its faces. So this is a standard line, just a standard import line that you need to do at the beginning of pretty well every code, every script that runs JavaPlex. Now we're going to initialize the simplicial complex. So generally, and in the tutorial, a simplicial complex, and more generally, what we'll learn later in a few weeks as a filtration, is going to be labeled with stream. So here, there's some technical syntax for this function API plex4 create explicit simplex stream is simply initializing what will become our simplicial complex. So now we construct the triangle. The triangle has 3 vertices, so we do that via add vertex. So add vertex is what to do to add a 0 simplex to the simplicial complex. And then for any higher dimensional simplex, we use this function stream.addElement. And then you simply add a higher dimensional simplex via a list of its 0 simplices. So here, this 0, 1 means we're adding a 1 simplex between the 0 simplices with labels 0 and 1. Then we add the other 2 edges, and we have the hollow triangle. And there are a few functions that you can call to get some information out of a stream, aka simplicial complex. Really, there's not much to this particular simplicial complex, so the only thing we can do is look at stream.getSize, and we see there are 6 simplices corresponding to the 3 0 simplices and 3 1 simplices. There's no visualization for simplices themselves inside of JavaPlex. That's not a built-in functionality. There, I think, is software that you can find out there for visualization of simplicial complexes, though a lot of that software is fairly tricky and would take a little bit of setup. So if that's visualization is something you're really invested in, then you could look into that online, and we may spend a little bit of time on that at the very end of the semester. We're not going to focus on that at this time. So this was a very simple example. Also, there's this line that you can see I have commented out right now, stream.finalize stream. So that's if later on we'll be doing things, with these simplicial complexes after we've defined them. And so if you want to set a simplicial complex in stone before, moving on and performing computations with it, you'll need to use this finalize stream command function. Now, let's look at a slightly more involved example. So this is what to do to create a hollow sphere. So again, we need our import line. we need to initialize the complex, same as before. And now we construct a simplicial sphere in dimension n. Here the dimension is 1. So first, we're adding element from 0 to dimension +1. So recall, in MATLAB, this notation, like 0 to here the dimension +1 is 2, that is simply the list incremented by 1 going from 0 to 2, inclusive at all ends. So this is like the same as adding an element with 0, 1, 2 in the notation from the previous example. Next is this very, very useful command, stream.ensure all faces. So in the previous video, we discussed, the example that if you have a set of simplices, it will fail to be a simplicial complex if all faces of existing simplices aren't contained in the set of simplices. This function, ensure all faces, looks at the current collection of simplices you have and adds in all missing faces so that you're guaranteed to have a simplicial complex. So very handy. Next is stream remove element if present. So this allows you to take a simplicial complex and remove an element. So we're removing the simplex that we started off with. And so if we go through just verbally, here we are adding the simplex 0, 1, 2. Then ensure all faces will add in the three 0 simplices, the 3 vertices, and it will add in the 3 edges between each pair of vertices. So at this stage, we have a filled-in triangle, and then we remove the 2 simplex in the middle. So now we have a hollow triangle, which, as discussed in the lecture, is homotopy equivalent to a circle, which is precisely a 1 sphere. This function validate verbose is something which can check if what you have present is in fact a simplicial complex. So now we are running stream.getSize again. So we run this, we see 6 simplices. Again, this is what we expect. This is actually the same as the previous example we had of just a hollow triangle. So 3 0 simplices, 3 1 simplices. And validate verbose is giving a logical 1, which refers to simply, yes, this is in fact a simplicial complex. So now if we comment that out, let's go down here and we'll add an element, which is the simplex 0, 1, 2, 3. So if we now add that simplex to our set of simplices and do validate verbose, what will happen is we'll see answer logical 0. So validate verbose is returning 0, meaning this is not a simplicial complex. And furthermore, validate verbose is very useful in that it tells you precisely what's missing. So we added this simplex 0, 1, 2, 3 in this line, but we didn't add any of its 4 faces. So this is very much not a simplicial complex, and validate verbose tells us that it's not a simplicial complex and tells us precisely how it is failing to be a simplicial complex. So very useful. And we can go back and make this any dimension. So we can say we want to construct a 10 sphere. So very, very high dimensional hollow sphere. We run this and we see there are 4,094 simplices now. And maybe you can do a little quick combinatorics and come to the conclusion that this is the number of simplices we should have. Anyway, let's move to one last example, which is on Viator strips. So here, there is a little bit that I'm not going to explain to you precisely, because JavaPlex doesn't actually define a simplicial complex for the Viator strips complex built in. It defines the Viator strips filtration, which is something that we haven't defined yet. So if that sounds completely new, that's fine. We haven't covered that yet. We'll be covering it in a few weeks. But a filtration consists of a sequence of simplicial complexes, so we can use a filtration to, I guess, get at individual simplicial complexes, so to speak. So now, again, we just need this import line and everything. We define the distance matrix that we discussed in the previous video. We worked through Viator strips simplicial complex on this distance matrix by hand at a few scale parameters. And now let's go through and use Viator strips built-in computation in JavaPlex to compute those same complexes. So here, first thing we need to do is take a distance matrix and convert it to a metric space that JavaPlex understands. So there we use this function, a metric.impl.explicit metric space. This is in the documentation tutorial PDF that was shown at the beginning of the video. Max dimension is just a variable which highlights what is the maximum dimension of simplices you should consider. So as I noted previously, if you take simplices of very high dimension in a Viator strips complex, the number of simplices in the simplicial complex can become very, very large very quickly. So this is a way of limiting that. Then max filtration value, that's something we won't really discuss for now. Number of divisions we won't discuss for now. Here's the important part. Again, we're defining a stream, and now we're using their built-in Viator strips function. So api.plex4.create Viator strips stream. The inputs are the metric space, the maximum dimension, the maximum filtration value, and number of divisions. Again, not really going into what those are right now, but those are required for this. For now, we'll focus on the first three. So max filtration value is set to 0 right now. So what that means is the simplicial complex, which exists at scale parameter 0, is what, in essence, this is going to create. So we run the software, and we see that the number of simplices is 4, because at filtration value 0, recall we just had the 4 0 simplices isolated. Now, we computed what the simplicial complex is at scale parameter 1, and that is going to be the 4 0 simplices, but then recall there's a central 0 simplex, and it's going to have one edge going out to each of the other 3 0 simplices. So we run this, and we see now 7 simplices, because the 3 1 simplices got added. And lastly, if we go max filtration value to the diameter of the space, we'll have all possible simplices. In particular, this will, as we said before, be the 3 simplex with all of its faces, which you can verify for yourself should consist of 15 simplices. So these are just a couple of ways to define simplicial complexes in JavaPlex for a good quick exercise. I recommend you play around, try to create a few simplicial complexes for yourself. Some good practice problems are to create the simplices K1 and K2 from the previous video in JavaPlex, and see if you can, define the simplex K first, and then go from K to K1 and K2 via some of the functions we've seen, built-in functions from JavaPlex we've seen today. And I'll tell you, there are multiple ways you can go about doing that, and so try to find them all. So that will be all for today, and in the next week, we will be discussing homology. So I will talk to you then.